So, okay, so now we are in the topic dynamics. So Newton's second law and application. So for the MCAT, you have like 20% or 25% of the question will cover mechanics. So the questions could be very simple, like this one, right? So let's try to do this one. It's just Newton's second law. You just need to know the equation. So this one is an easy equation. So you have two ways to write Newton's second law. You can say F equals ma, okay? So that's one way. Or you can use the impulse momentum theorem. And the impulse momentum theorem says that if you apply a force during a time t to a mass m, its velocity will increase or decrease, depending if it's opposing motion or not. So this physical quantity here is called the impulse. This physical quantity is called it's the change in momentum. Momentum is just mass times velocity. Okay, so it just says that the impulse delivered to an object. So if there is an impulse delivered to an object, then it will change its momentum. So those it's the same. So originally Newton wrote his second law this way. So this is called the impulse momentum theorem, but it's the same thing, right? Because I can write the acceleration as delta v over delta t, and I will get this. Okay, so in that case, so it depends on the problem. So in that case, you want to use this one. You can use the other one also, but it's easier. You will go faster. Okay, so let's do it. It's easy. So you have it's a linear motion, and you have some rocket ship. I don't know how to draw rocket ship, and you have the mass, which is 1,000 kilograms, and you have an initial velocity of 100 meters per second, and then it's you have a force. So there's a force applied. So there's a force applied here from the engine. Okay. And so therefore you're going to have an acceleration, and you apply that force over 8 seconds. Okay. So now it's going to be here. And obviously the speed, it's going to increase, right? So it's 100 meters per second. So you have an increase in speed. And the force here, average force, so we say, okay, so the net force is constant. You average it, so the acceleration will be constant. So what is the change in velocity? So they want you to know delta V. So you're going to write the force and the time elapsed. So here you start your stopwatch here. The time elapsed is 8 seconds. So it's very simple. Equals m delta V. So the force here is 20,000 times the time is 8 equals 1,000 delta V. Okay, so you can cross this out, and so delta V will be 160 meters per second. It's a very simple problem here, just to review the basics. Okay, so as usual, you want to pause the video. Okay, next one. So it's the elevator. So you want to make sure to read the question very carefully, because sometimes it could be confusing. So you can pause the video here So you have an elevator, okay, and maximum weight. So a weight is a force, okay. So the weight pulling down is 9,800 Newton, and it's moving at a constant speed. Okay, so the speed is constant. So if the speed is constant, that means the net force is zero after an initial period of acceleration. So of course, during that period, that means the tension has to overcome the weight, and then it's constant between the maximum tension of the elevator and maximum weight while it's accelerating upward. Okay, so if it's accelerating, so if you do have an acceleration here, that means the net force has to be up. Acceleration and net force have the same direction. So it means this is your elevator with its load. So if the acceleration is upward, that means the net force has to be upward. So that will be the tension. That will be the weight. Okay? So the net force has to be upward to provide the acceleration here. So that will be the net force. Okay, so the net force will be the tension minus the weight. That will be equals to ma. So if you want to have an acceleration, that tension has to be larger than the weight, right? So tension will be mg. So first it has to balance out mg, weight, plus it needs to provide some acceleration. So that means the tension has to be greater than mg, has to be greater to provide the acceleration. So the net force is upward, okay? So net force is always parallel to the acceleration, and in magnitude, it has to be proportional. Okay? Okay. And that was not bad. So let's do the next problem. Okay. So these are inclined plane. So inclined plane, there is a few things, like at least two things that you need to memorize. So you don't, and if you want to know why, you can look at my lecture. But it's easier to memorize for inclined plane. So if you have an inclined plane here, that will be an inclined plane. And then the angle here is 30 degrees, or could be alpha. Yeah. And you have a box, a wagon. So it's a wagon, 10 kilogram. And so anything on the inclined plane, whether you have friction or no friction, apply force or no apply force, you always take the axis here, the x-axis along the inclined plane. Doesn't matter which way is positive, negative, but what's going to happen, you always have the component of the weight trying to bring it down slope, and that component is always mg sine 30. That's what you need to memorize. Okay, so you always have that mg sine 30, and then you have another component of the weight here, mg cosine 30, and usually it's balancing out the normal force. You always have the normal force here. Normal means perpendicular, so perpendicular to the normal, to the inclined plane. You always have a normal force. And you see that will be your weight here. So that will be your weight down. But the component of the weight, that's what you want to memorize. So mg sine is trying to make the wagon sliding down, and that will be the component of the weight balancing out the normal force, right? Then you can add friction or apply force. So in that case, you have an apply force here. So someone is applying a force. So we have students here applying a force here. F applied. And to make sure it doesn't move, the force applied has to be equals to the mg sine. Okay. Okay. That's so a force applied in that case will be equals to mg sine 30 degrees. And sine 30 degrees is sine 30 degrees, it's going to be 0.5, right? So this is 0.5. So it's going to be the mass 10 times 10 times 0.5. So the force applied is about 50 Newton. I took G equals 10, but you can take it to 9.8. So that B here, that's going to be the answer. Okay, so let's look at the other question. So those questions are not that hard. So we want to know. So here you have to be careful with the question as well. So again, you can pause the video. You can pause the video, and they are asking you about units. So again, the impulse momentum theorem, SI base units for each variable. So you want the SI base units. So you want to know which of those expressions correctly represent the SI base units for each variable for that equation here. Okay, so here it doesn't work because in SI unit, you want to know, you need to have kilogram. So that, even though it's consistent, so you can cross this out, you have gram meter per second, and you have gram meter per second, and this is mass, and this is speed. Okay, so that could work, but gram is not a SI unit. Okay, so here works too, because mass is kilogram, meter per second is speed, and that will be second. And this here is the unit for force, right? So the force, unit for force, if you remember, F equals ma. Okay, so it's going to be mass, and acceleration is meter per second per second. So that could work. And then this one doesn't work. It's not SI unit. And anyway, mass is not a force. Pound is the British unit for force, and mass is not a force. So that doesn't work. What about this one? Mass, yes, meter per second. And then the force is in Newton and the time is in second. So it has to be this one, because in SI unit, the dimension, the unit for force is Newton. So the answer will be D. Okay, so let's do this one here. So here we have rotational equilibrium. Rotational equilibrium. Oh, that was the impulse momentum theorem for my slides. Okay, so equilibrium, you see that the torque applied by F1, so it wants to apply a counterclockwise torque, and this one will be clockwise torque. So here we have an equilibrium. When you do have an equilibrium, the relationship is easy, right? You have that distance times F1 equals this distance here times F2. So you just have to remember that. It's not that hard. Okay? So always you have your drawing here. So you have a seesaw. And what does it say? You have a fulcrum somewhere. So you have a fulcrum somewhere. 2 meters. So that will be 2 meters. And the mass here is 30 kilograms. So of course, the force will be the weight. Okay, so the weight here, which is mg, but it doesn't matter. We can keep in kilograms because it's an equilibrium. So 30 kilograms on one side, and the dad 90 kilograms. So it has to sit closer. 90 kilograms. So the ratio is 1:3. So it has to be closer, okay, by 1/3, right? So that distance should be 1/3 of this one. Or you can say 30 times 2 equals 90 times x. So let's find that distance here. So x will be 30 times 2, 90, which is 2/3, which is 0.67. Be careful with the units here. We have meters, so that will be meters. So it should be 67 centimeters, right? So that should be 67 centimeters. So the answer is, so you need to draw the situation, which makes things easier. Okay. So let's look at the next one. With friction on the plane. Okay, so let's look at the options here. So again, you should stop the video and try to do it. For movement on the plane with friction. Okay, so it's a little bit tricky. You have to be careful. So you have something on the rough surface, which means you're going to have some kinetic friction. So kinetic friction is the coefficient times the normal force here. And if there is no angle, if it's not an inclined plane, the normal force is just mg. If it's an inclined plane, the normal force is mg cosine. Acceleration depends only on the applied force, no? So let's see, you are pushing here. So that will be F applied. But you also have some friction opposing the motion here. So the acceleration by definition is the net force. Okay, so it will be the force applied minus the friction. So it doesn't depend only on the applied force, obviously. A greater force is required to start accelerating a stationary, so it means it's not moving to begin with. Okay, so that here, it's because when you try to get something moving, you have to overcome the static friction. So to get it moving, it's always harder to keep it moving. So static friction is always larger than the kinetic friction. So yes, this is true. The frictional force remains unaffected by the mass of the object. That's not true, because if you increase the mass, of course, it's the two surfaces is going to hook more together, and it will be harder to push, right? So by the way, you see here the kinetic friction equals the coefficient times mg. Static friction is a different thing, because as you push, it's going to push back on you. But kinetic friction is proportional to the weight in that case. So yes, it is affected by the mass. So that will be B. Only 2. Okay, so the answer is B. Okay, so let's do this one. So you can stop the video and try to do it. It's, again, all those problems are simple, very simple. So this is dragged. So that object here is dragged by a tension T. So here it says at a steady pace. So steady pace means the velocity is constant. So it means the acceleration equals to 0. So it means here, so no acceleration. So you always have, when you have a motion here, you're going to divide the forces into its component. So it's only along the X that is moving, along the Y, it's not moving anywhere. So the tension has 2 components here. So that will be your X component, and that's going to be your Y component. So if it's moving at a constant velocity, that means the X component of the tension equals the frictional force, which is a kinetic friction. They are equal to each other, right? And that here will be component here, it's the X component, that will be T cosine theta equals, okay? Okay, so the answer will be D. And you want to make sure you see that it's a steady pace. So it means that the velocity is constant, so the acceleration equals 0. Okay? Okay, let's do this one. It's a problem with rotational equilibrium left of the fulcrum. So this is your fulcrum, and you apply a force F. That distance is 0.6. So this is in Newton. And now you are placing at 0.4. So 0.4, and you have a mass m, and that mass m is 10 to the negative 7 kilogram. So we have to be careful because this is in Newton and this is in kilogram. To get from kilogram to Newton, so it's consistent, then you need to consider the weight, right? So mg. Okay, so the weight here, it's going to be 10 to negative 7 times 10. So the weight here, it's going to be 10 to the negative 6 Newton. Okay, otherwise, it's not consistent. If I have kilograms on one side, I should have kilograms on the other side. Newton on one side, you have Newton on the other side. So then it's easy once you clear this out. So it's going to be the force times 0.6 equals 0.4 times 10 to the negative 6. So the force is 0.4 times divided by 0.6 times 10 to the negative 6. So that's 2/3, right? So 2/3 times 10 to the negative 6. So it's going to be 0.67 times 10 to the negative 6. So it's about 6.7 times 10 to the negative 7 Newton. So it's just to make sure you know your scientific notation. So the answer will be this one. Okay, so let's do the next one. So in this situation, you have an inclined plane. Okay, so it's an inclined plane here, and the box goes from A and then to B, and then it keeps sliding to C. So you have the box here, and it's going down the inclined plane, keeps sliding, and at some point it's going to stop. So you have here the velocity as a function of time. So it starts with velocity A, and then the velocity it's given to you. So you have to interpret the graph. The velocity is going to increase, and then velocity is going to decrease. And at some point, it's going to stop. So that's the meaning of the graph. You will have to interpret. So here they talk about the work. We didn't cover work yet, but to answer this question, we don't need to cover work yet. So it just says that the work done by friction from A to B equals mgd. That's what it says. But anyway, here is the question. How will the work change? So the work done by friction, so going down here, going down the slope, you're going to have friction opposing the motion here, so it's going to be kinetic friction. And remember, you always have the component of the weight pulling down slope, okay? And you have another component of the weight here, mg cosine, which is balancing out the normal force. So the kinetic friction, in that case, kinetic friction is a coefficient times the normal force. But on an inclined plane, you can memorize it. The kinetic friction is the coefficient times mg cosine alpha. So the kinetic friction depends on the mass and also on the slope here. Okay, so you see as the slope is going to increase, the kinetic friction here is going to decrease. So anyway, they're asking what's going to happen to the work done by friction if the initial speed is doubled. So a work, we're going to see that next, but a work is the force times a distance. Okay, so the distance is not going to change if you change the velocity at point A, and the kinetic friction is not going to change either because it only depends on the mass and on the slope. So in that case, the answer is will not change. Okay, so it looks challenging because you see a graph, but Actually, it's not that hard. You do have friction between A and B. So at point A, it has energy, it has kinetic energy, potential energy, and so some of the energy will be lost because you have friction. You end up with some kinetic energy here, and then everything is lost to friction. Okay, so next question here. So here you don't even need to know the physics for that. You just need to know the math and units. So let's go back to the graph here. And they want to know what's the physical quantity, okay, shown by this area here. So you have an area. So you could divide the area into geometric shape here. So you have a square here, a square here. So if you add all those little shapes here, what's going to be the physical quantity? So area is always 2 dimensions, right? So you multiply width times length, for example. So what are the 2 dimensions involved? You're going to have the time here, and here you have the speed. So meter per second, and then times second. So if you do meter per second times second, it's going to be meters. And the only thing that sounds right here will be the distance. So just by looking at the units, you can answer the question. Now, if you do a little bit of derivative or calculus, you know that the velocity is dx over dt, right? So dx equals v dt. So the distance covered, okay, it's the integral under the function v from point A to point C, and you can divide those two shapes, but in 2 shapes, okay? Okay, so it's an interesting question because you just need to look at the units, okay? Sometimes it's very important to know the units for the physical quantities. Okay. And then the same question. So it's the same question here. Same problem of an inclined plane. And so you can pause the video and try to answer here. Okay, so next question here. You have to read very carefully because it says from point B to point C. So the box is going down slope here, and then it's going on a horizontal line from B to C. So from B to C, you see that the speed is decreasing, and it's going to decrease until it's going to stop here. At that point, it's going to stop. So you see the slope is negative, which means there is an acceleration, but it's a negative acceleration. So if there is an acceleration, there is a net force. So what's going to happen, you can stop the video, but it's going to slide down. Okay, so again, it's going to be acted upon by, just to review, you have mg sine down, and then you have some kinetic friction here. Okay, but it's still spinning up. And then you also have the mg cosine. Okay, and that will be balanced out by the normal force, right? So in that case, from here to there, the kinetic friction is in magnitude the kinetic coefficient times the normal force, which is mg cosine. But once it's gonna reach the bottom here, so sliding from B to C, so the only force opposing the motion here, there was only one force, and that will be that force here opposing the motion, which is the kinetic friction. Okay, because down you have mg, and up you're going to have the normal force here. So here you have normal force, and here you have mg. So the kinetic friction equals, in magnitude, the coefficient times the normal force. So it's going to be the coefficient times mg. Now, acceleration, that's what they want. They want you to find the acceleration, which is the net force. So net force divided by the mass. So it's going to be, in that case, over the mass. And I should put a negative here if I talk about the direction I hat. So I suppose I hat will be in this direction, so just positive x-axis. You can cross this out. So the answer is this one. This is just the coefficient of friction. See, it says the coefficient of friction. Okay. So we did that. Okay, what's going to happen to the frictional force if the angle of the ramp relative to the horizontal is increased? So you can pause the video, but what's going to happen if you increase that angle here, right? So you have an inclined plane again, and have an inclined plane, and you have your box here. So you're going to have the coefficient here of friction, and down there you have the component of the weight, mg sine. So the kinetic of friction is the coefficient times mg cosine. Okay, that actually is the magnitude of the normal force, right? So that will be the normal force you push on the plane. The plane is going to push back on it. So mg cosine. So you see that if the angle increases, the cosine will decrease, and the coefficient, the kinetic friction will decrease as well. Because at worst, if you make the angle very, very large here, like this, you can see that it's not going to push as hard. And the box is not going to push as hard on the plane, so the plane will not push as hard back, so the normal force will be very small. At worst, if it's like 90 degrees here, it doesn't push at all, there is no friction applied, and it's just going to be in free fall. So the answer for that is it will decrease as the normal force on the ramp surface will diminish. Okay, so that's for that question here. Next one, it's an experiment done to analyze, to look at the kinetic friction again, okay, or static friction, because at some point it's not moving, and as you increase the weight, it's going to start moving. So that will be kinetic friction. And they give you some results here for the experiment done. Okay, so that will be different material used. This is the block here. That will be different area. And so that will be the mass that you need here to put, so you can overcome static friction, and it's going to start moving. After the block starts sliding, how did its speed change over time? So once it starts sliding, So once it starts sliding, it's gonna speed up, right? So, but when this block here, when it starts sliding, we suppose it's gonna speed up, okay? So it has two forces applied to it. So you can stop the video, by the way, and try to answer the question. You should pause the video. So it has, because the acceleration is constant, it says somewhere here that when it starts sliding, it's going to accelerate. That means the net force is constant. So you're going to have the tension here and you have some kinetic friction. So the kinetic friction is the same. The tension is the same. So the applied force is the same. So the acceleration will be the same. So if the acceleration is the same, so then we have V equals AT, right? So the velocity will change linearly with the time if there is a constant acceleration. So the answer is the speed will increase linearly with the time. Okay, so describe the relationship between static friction and the base area. So let's look at here. Let's see if the base area matters. So here you have one base area. So then you take a larger block and then you take a larger block. Always testing the same material. So if you look at this area versus this area versus this area, so you increase the area, you see that the threshold mass it does not change, right? It stays the same. And likewise, if you look at another material and you increase the base area, you have here 0.068, 0.068, 0.068. So it doesn't matter the mass, the base area doesn't matter. The threshold mass, okay, will be always the same. Okay, so it means the static friction will be always the same. So the friction does not depend on the area of contact. Okay. So if you want to find the experiment that we do usually to find the coefficient of friction, the static friction force on the block, which are the following measurements you will want to take. So if you have an inclined plane here and the block does not move, the experiment is that you're going to increase the angle here until it starts to move. So when that happens, when it starts to move, okay, when that happens, it means that mg sine balance exactly equals to the static friction. Okay, so the static friction will increase until it cannot no more increase. So in that case, we have that the static friction, okay, will be equals to mg sine alpha. And again, the static friction will be the coefficient here, the static coefficient, okay, times the normal force, which is mg cosine equals mg sine. You can cross this out. So you see that the coefficient of static only depends on the angle. Okay, and it makes sense. Okay, I think that's it.